Welcome to bmac math tutorial. Subscribe our channel and hit the bell icon for freshly uploaded contents. This is a question from CSIR NET December 2019. In this problem, we are given a function uxy is a solution of the Laplace equation del 2u del x2 plus del 2u del y2 is equal to 64 in the unit disc and such that u vanishes on the boundary of the disc. Then it is asked that what will be the value of u at the point x is equal to 1 by 4 and y is equal to 1 by root 2. Although this problem is prescribed at the Cartesian coordinate system, but since this problem is related to unit disc, therefore we need some preliminary knowledge of the polar coordinate system. First, note that the Laplacian operator in Cartesian coordinate system is given by del 2 is equal to del 2u del x2 plus del 2 and del y2 in Cartesian system, and in polar coordinate system the Laplacian operator is given by del 2 del r2 plus 1 by r del r plus 1 by r square del 2 del theta 2. Now the given problem is del 2u del x2 plus del 2u del y2 is equal to 64. If we transform this equation into polar coordinate system using the transformation, x is equal to r cos theta and y is equal to r sin theta, then the equation 1 reduces to del 2u del r2 plus 1 by r del r del u del r plus 1 by r square del 2u del theta 2 is equal to 64. Now since this problem is related to unit disc problem, then using angular symmetry we can neglect the term 1 by r square del 2u del theta 2 from this equation 2. Hence the equation 2 reduces to this form del 2u del r2 plus 1 by r del u del r is equal to 64. Now if we multiply r throughout this equation, we have r del 2u del r2 plus del u del r is equal to 64 r. Now this left hand side may be written as del r r del u del r is equal to 64 r. Now integrating, we have r del u del r is equal to 64 into r square by 2 plus some constant c. C is a constant. Now, since the harmonic function u is symmetric about the r axis, we assume the condition del u del r is equal to 0 at r is equal to 0. This condition is known as the symmetric condition. Using this condition, we can calculate that the constant c is equal to 0, and therefore the equation 3 reduces to r del u del r is equal to 32 r square, which implies del u del r is equal to 32 r. Again, integrating, we have u is a function of r is equal to 32 r square by 2 plus some another constant, say c1. c1 is another constant. Now it is given that u vanishes on the boundary of the disks. Therefore, we have the condition ur is equal to 0 at r is equal to 1. Using this condition, we have c1 plus 32 into 1 by 2 is equal to 0. This implies c1 plus 16 is equal to 0, which gives c1 is equal to minus 16. Hence, the solution in polar coordinate system may be written as ur is equal to 16 r square minus 16, which is equal to 16 r square minus 1. Now in Cartesian coordinate system, we have the solution uxy is equal to 16 x square plus y square minus 1. Now at x is equal to 1 by 4 and y is equal to 1 by root 2, we have u 1 by 4 1 by root 2 is equal to 16 1 by 16 plus 1 by 2 minus 1. This is equal to 16. LCM becomes 16. 1 plus 8 minus 1. This is equal to 16. 9 by 16 minus 1. This is equal to 16. the LCM becomes 16. 9 minus 16, this is equal to 16 into minus 7 by 16, which is equal to minus 7, and hence the correct option is option 3.